Okay, this is lesson 5.3b. So mainly graphing logarithms. We've talked about logarithms, but we haven't graphed them. So they have an asymptote similar to exponentials, but it's a little different. You'll notice the difference right away once we start plotting a few points here. So this is a parent graph. I need you to memorize a few of the points, actually only 1 point, but the behavior you need to know really well. So let's plug in some points here. So 0, 1, 2, 3. Actually, just let's do 0, 1, and well, let's just start with that. Okay, so 0, let's do that. So that this would be the log base 2. Let's just do 4 also. Log base 2 of 0. So basically, if we're trying to figure out what is that equal to, we're like 2 to the what power is 0. 2 to the 0 power is 1, but 2 to the what power is 0. There is no such thing. It looks like we can't plug in 0. Well, that's interesting. Huh. Okay, so let's plug in 1. So log, this is one of our properties, by the way, log base 2 of 1. 2 to the what power is 1, and that would be 2 to the 0 power. So 1, 0 is the point I need you to remember. That is the famous point I need you to know. This would be log base 2 of 2. This is also a property. 2 to the what power is 2 to the first power. So 2, 1 is the point on the graph. Let's plug in 4. That'll be a good one to do. Log base 2 of 4. 2 to the what power is 4. That would be 2. So 4, 2 is the point on the graph. Looks almost like, oh, looks kind of interesting. Okay, so let's plug in 1/2 here. So this would be log, this is kind of weird, of 2 to the 1/2 of 1/2. So that's 2 to the what power is 1/2, and that's actually to the -1 power. You'd have to bring it down, it needs to be negative. So 1/2, -1 is right about here. If you plugged in 1/4, that would be log base 2 of 1/4. 1 over 2 squared. I'm going to write it that way just so you see it. So 2 to the what power is 1 over 2 squared. That would be the -2 power. So 1/4, -2 right about there. You probably can kind of see what's happening with this graph. So the graph is kind of coming down. It's getting closer and closer to that line. So there's no horizontal asymptote on this one. There is a vertical asymptote at x equals 0 because you can't plug in 0. Oh, I haven't tried to plug any negatives yet. Let's plug in some negatives. Let's do -1 and -2 here. So this would be log, sorry, -2. This would be log base 2 of -1. So 2 to the what power is -1? I don't know. Log base 2 of -2. 2 to the what power is -2? I don't know. In fact, I would say those two things are impossible, which kind of leads us to our domain and range. So our domain on this is x greater than 0. Can't take the log of 0, can't take the log of a negative number. Range looks to be all reals. So range can be anything, goes up forever to the right, goes down forever, but it doesn't. Okay, we'll get to that kind of stuff in a minute. Okay, so let's look at this. So log 2 of x plus 3. So we're going to start with our parent graph that hopefully you have memorized by now. We just had it, but here's the basics you need to know. Asymptote, x equals 0. Crosses through the point, 0, 1. And the behavior of the graph, something like that, roughly. Okay, what do you think that plus 3 does to the function? So let's just talk about transformations for a second. Y equals a times log base, I don't know, b of x minus h plus c. So you can see that h is going to move it right or left. C is going to move it, plus k, I guess, sorry. Plus k, I don't know why I said plus c. So this one definitely is going to move it to the left. So every point is going to move to the left 3 units. So you take that asymptote, it's now at x equals -3. Draw that first. The point was at 1, 0, now it's -2, 0. And the graph approaches the asymptote over here, kind of does that, something like that, roughly. It's pretty good. It's the basic behavior. Okay, we start with the parent graph. x equals 0. Point right there. Graph has this kind of a look to it. That's the parent graph. Okay, so this one, it looks like all it's doing is just moving everything up 3. Moving a vertical asymptote doesn't really change it. It's still x equals 0, but this point now moves up to 1, 3. So the graph will look roughly like this. Okay. Asymptote, x equals 0. Got a point here at 1, 0, behavior, something like that, roughly. Okay, and so what the negative does, this is kind of a weird one, but it's going to reflect over the x-axis, right? So this point, so all these points, like this point that was at kind of 2, 1 is now at 2, -1. It was at 4, 2, now it's at 4, -2. So the graph is approaching the asymptote this way. Okay, so here, this is going to be reflection over the y-axis because it's not in front of the function, it's attached to x. So everything gets reflected over the y. So that point moves to there, the asymptote stays the same. It was at 2, 1, now it's going to be -2, 1. Was at 4, 2, now it's going to be -4, 2. And the behavior of the graph is, it's not beautiful, but that's what it does. Something like that. Find the equation. So this time you're given very similar to what we did with the logarithms, right? So don't plug in this point because that is like every logarithm graph goes through 1, 0 pretty much to start with. So plug in, like this one would be your x and y, plug in those values. So y would be 2, and this would be log base, I don't know what a is, of 9. So now maybe to solve it, typically what we do to solve is we put it in the other form, right? So let's put it in exponential form and see if that will kind of make sense to us. So it'll be a to the exponent is always the other side because log is an exponent. So a to the second equals 9. So what is that? What to the second power is equal to 9? A must be 3. Therefore, my equation is y equals log base 3 of x. Let's try another one. This one might be tougher. Okay, same thing. We have y equals log. There's no transformations on this one. It's just a basic graph. I would definitely, choose this point as your x and y. It's going to be a little tougher to solve. Let's see what happens. -1 equals log base a of 1/2. So we get a to the -1 equals 1 over 2. A to the -1 is really 1 over a equals 1 over 2. I probably don't even have to solve at this point. Can you tell that a is equal to 2? And so the equation would be y equals log base 2 of x. Did I write the equation last time? Yeah, I did. Find the domain. So remember, you can't take the log of 0. You can't take the log of a negative number. So we know whatever's inside of there, in this case, x minus 4, must be greater than 0, not equal to 0. A little different than square roots. Remember, square roots can be 0. These have to be positive numbers in order to be able to take their log. So x minus 4, that quantity must be positive. Just take one step to solve that. So x greater than 4 would be our domain there. And by the way, the graph, I mean we don't have to graph it, certainly in this one. But so the parent graph, would look roughly like something like that, goes through 0, 1, has asymptote at x equals 0. If I move this to the right 4 units, which is what that transformation does, the point moves, the asymptote moves. It's now x equals 4, and the graph is going to look kind of like that roughly. So you can see that the domain actually is x greater than 4 because the whole graph moved to the right. Instead of x greater than 0, which would be the normal domain, that's what it'd be. This is kind of neat. So let's just graph these two. Once you make a connection here, maybe you'll see it. So the base on this one is 2. So let's see, that's our parent graph, right? Goes through that point, that point, that point, has this kind of a look to it. Approaches an asymptote at x equals 0. It's a vertical asymptote. Okay, and let's do this other graph in red. So we do this one in red. This graph, oh wait, you know what? I just did the wrong one, wrong color. Let's start over here. So I was just in, I'm so much in a mode of doing logarithm graphs that I've got to switch mode here. So just clear out those couple points. Okay, so an exponential graph, sorry about that. Exponential graph is going to be, the parent graph has an asymptote that's horizontal. It's going to be y equals 0. It goes to the point 0, 1, and the graph, goes through like this point. I think it goes through that point. So like something like that, roughly. I think that's pretty good. And then the log graph, which I just did a minute ago, has a vertical asymptote at x equals 0. Crosses through this main point. It's this point. I think this point roughly looks like this. Okay, and I don't know if you see the relationship there. You might even see that if I were to draw like a dotted line here, I didn't draw that very good. Try to draw it through the. Oh, that's better. That line, by the way, has a name. It is called the identity line. So this is the line y equals x. It's the identity line. If you reflect across that line, right, you get the inverse function. I don't know if you see it, but the base on this one is 2. The base on this one is 2. They have the same base. These functions are exact inverses of each other. You might be wondering, why are we doing exponentials and logarithms in the same chapter? Because they are inverses of each other. Let me prove it. So what's the big idea of inverse? Remember how to find an inverse? You can say, instead of f of x, I'm going to say y. So y equals 2 to the x. I'm going to switch x and y to find its inverse. So x equals 2 to the y. That actually is this equation right here, but it's not the right form. Let's solve for y. The only way to solve for y is to put this in the log form. So I'd say log base 2 of a number, in this case, x, is equal to the exponent, which is y. Look at that. You get that equation. If you find the inverse of 2 to the x, you get log base 2 of x, or vice versa. They're inverses of each other. So that's kind of a neat thing. I could rename this. I could say this is the inverse function there of f. Because it is. They're definitely inverses. You can even see like the point, the order pair here is like 2, 1. The order pair here is 1, 2. The asymptote is y equals 0. That one's x equals 0. Remember the big idea of inverses? X and y switch places. So everything's just kind of like backwards, and it just looks like that. That's good. That's the lesson. Let's look at the PSAT. I think we have time. There we go. So it shows the top view of an open square. Twice the area of the smaller rectangles or squares there. When a marble is dropped in the box, it falls into one of the compartments. What is the probability to fall into F? So this looks like it's taking up, if I broke this into like 9 equal boxes, because that's twice as big, there would be 2 ninths. So I think 2 ninths, I don't know if you see that, I just kind of see that relationship there, because the rectangle is twice as big as the square there. So you just kind of think it through and get it. That's it.